Okay, hello. This is our project presentation for STAT 6000.
I'm Madison Evans.
I'm Mike Brown.
I'm Chonghe Wang.
And I'm Xiaowei Huang.
And our problem definition, we're asked to select a data set to analyze. And the data set have to be at least 10 predictors and 100 data entries have to be enough size. And we have to use the statistical method which we have learned in class. And we have to compare the method we chosen from and report what we're finding.
So after a little bit of research, we decided the best data set for our purposes would be, it's a red wine. It's actually a wine data set. And we decided we were going to use the red wines because it was a really nice data set that had a lot of entries in it. So it gives the information about quality of certain red wines based on different factors. There's 1,599 entries of 12 different variables. And luckily for us, the data was already clean. There was no missing values and there was no null values. So after checking for null and missing values, the data cleaning process was pretty simple. The data set contains both continuous and discrete variables, mostly continuous, with the quality variable being our discrete variable.
And we can see in the bottom part, the dataset have 11 predictors. And the response variable is to describe the quality of the wine. And it is a categorical variable because it's based on each predictors.
In order to better interpret our results, we decided to change the original quality variable to a quality variable that was 0 or 1. 0 meant that the wine was bad and 1 meant the wine was good. And the threshold score was a 6.5. So if it was above 6.5, it was considered good, and below 6.5, it was considered bad.
Each predictor versus different response 0 and 1, except for residual sugar, chloride, and free sulfur dioxide and pH value. And the average of the test error of the tests are different between good and bad wine. Also, there are lots of outliers, and it may be a reason of misclassification.
Because our predictor was categorical, we needed to use classification methods, and we chose 4 so that each of us got to practice at least one method. So we selected the QDA method, LDA, KNNN, and random forest classification tree. We also wanted to make sure that our model was that the test error was good for each model and not just check the training error. And because we didn't have a specific data set for a test data set, we used a resampling method. We chose the K-fold cross-validation resampling method because it wasn't too computationally difficult, but it also would give good results. And this method splits the data into 10 different folds that will be used as training and test data.
And let's begin with the first method, LDA. And we assume the variance of each class are the same, and the means and the variance are both estimated. And we can see the graph. We're using LDA to reduce the 2-dimensional graph into one-dimensional graph that we create a new axis. And after creating the new axis, we'll project each data point on the new axis. And in my work, I created a LDA model by using the LDA function under mass package. And this is the details showed by the result. And we can see like because we modified the raw data, we turned into the threshold value was 6.5 and we turned into 0 and 1. We can see there are almost 86% data are lying in the 0 class. And then we can see other values such as means of each attributes. And at the bottom part, we can see there is only one LDA1 model because we have modified the raw data. If we didn't, there will be several LD models. And this graph is the two distribution of the data set. And in LDA, the test error is 0.0875, which is very small. And because there are only like 2 classes and the variance is close to each other in comparison to the raw data.
The next method was QDA, and QDA is an alternative approach to the LDA, and that it does some of the similar things, but has a few differences. The main difference is that it assumes that each class has its own covariance matrix, and the decision boundary is more of a quadratic function, as you can see in the graph, which makes it more flexible. The differences between the QDA and LDA lie in the bias variance trade-off. And for my model, I showed a set, like the model for one of the sets of data. And you can see very similar to the LDA, 86% of the data was classified as bad, which is good because it matches the LDA, very similar to that. The mean test error of the 10 folds for the QDA was 0.1489.
So the next model we decided we were going to do was KNN, or K nearest neighbors. And basically what's going on here is you identify K nearest points for a given test observation. And based on conditional probability, the KNN will assign it to a group. And of course, as you go through and you change the number of K, you'll get different results. And basically the purpose of changing your K would be you're looking to obtain a good bias variance trade-off. So usually when your K number is lower, you have a more flexible method, but overfitting can be a problem. And when you raise the number of K up, you become less flexible and add a little bit more bias into the model. So one common approach is to use the square root of n, which is the number of observations for your K. So in our case, that's 39. So I tried K equals 39. And I also tried K is 5 and K is 10, just trying to get a lower number and then a little bit higher number to see which one performed better. As you can see on this graph, the K-fold cross-validation gave us 10 error points for each K, and they're graphed here. The blue line is K equals 39, the red line is K equals 5, the green line is K equals 10. And you can see in general, the red line performs a little bit better. So we can determine that the more flexible model is performing better in this instance with the error score. The performance of the model, like I said here, the K equals 5 provided the best results. So because the KNN provided 10 different data points for error, we took the average of the 10 different data points, and that was our test error. So K equals 5 provided the best error rate for the KNN, which provided 0.887 accuracy and 0.113 test error, which again, like the other models, is a pretty well performing model.
There are two important parameters which are the number of split candidate and the number of trees. So so we are going to do the three main steps. The first one is decide the number of trees, and the second one is build a random forest with different n, which means the number of split candidate. And then we check the importance of each predictor in order to improve our test error. So first, we randomly select a combination of training and test set. And from the right picture, you can see that the error become more stable after 200 trees, even though the typical decision is 500 trees. Then next, we do the interaction for getting better M. We build random forest model 11 times with each test and training subset. For M is equal to 1 to 11. And then we compute the average of test error for each M. From the left plot, you can see the dashed line means the average test error, and in M is equal to 6 is the lowest error, the lowest test error. However, when you check the test error for each line, M equal to 4 is the lowest test error for most lines. Then those M is equal to 4 and 200 trees are our final choice. So now we check the importance of each predictor in order to improve our test error. We noticed that the pH value and free sulfur dioxide are less important than other predictor. Then we are gonna rebuild rebuild 3 random forest model without pH value, free sulfur dioxide, and both respectively, and check their accuracy. And from accuracy, from checking the accuracy, we get the lowest test error is the model without pH value. So our final decision is build the random forest model without pH value. And we also check the table between true response value and the prediction. From the left table, you can see that when the response is equal to 1, it's easier and get more wrong prediction.
So after we computed all of our models, we decided it was time to compare each one to see which one performed the best. The QDA has about an 85% accuracy with a test rate of almost 15%. LDA is around 91 with a error rate of 0.0875. KNN 0.88 with a test error of 0.11. And Random Forest had accuracy of 0.918 with an error rate of 0.08. So here, just basing off of accuracy and error rate, Random Forest seems to perform better, and we think that may be because we're able to do a little bit of variable selection in Random Forest. But when you're deciding what model to use, there's also other factors you have to consider. You have to consider which model is most computationally large, or which one's most computationally complex. You have to decide which one can be interpreted more. So these are things you can think about. So Random Forest performs well here, but in more analysis, we may decide, since all of the values are so close to each other, that LDA may perform better because it's easier computationally to build, and it's less complex. It's easier to interpret results. So we think with more analysis, the model that we pick may change.
We wanted to talk about things we could do differently the next time if we were to go through this analysis again. One thing is looking closely at outliers to make sure they're not causing misclassification. Another thing would be looking at the results if we used the original quality instead of creating the 0 and 1 variable. Like we mentioned with random forest, there seemed to be some input variables that were not relevant. And so we would like to do further analysis to see which input variables are relevant and build a new model with only the relevant variables.